Okay, so last time we finished this theorem, approximate valuation theorem, which tells you that for a set of valuations and multiplicities and offsets, you can find a common function u, such that valuation of u minus ui is at least mi. So this sets up a approximate correspondence of rational functions and zeros or poles with multiplicity. So to study that in a big way, we define the divisors of a curve. So this is a new object. So this is basically you take these primes or these points on the curve. So the point P, remember, will always refer to a DVR. Okay, in other words, if you look at the unique maximal ideal of this DVR, it will be a uniformizer. So we will think of the point, the uniformizer, the prime ideal, all these things are the same for us. So this P is then a complicated object, and we are actually taking combinations of these linear combinations, but only integral. Okay, so 2P1, for example, this P1 plus P2 and P2 minus P1, these are things which are now available to you. And what is their physical interpretation is not clear. But surprisingly, this object will be highly useful in the analysis. Any questions? Okay, so this is called div C. We have defined, of course, we have defined divisor, which is an element of this div C. We have defined order map, which tells you what is the coefficient of the point in the divisor D. So this AP. So for D it gives AP. That's order. Order is a group homomorphism. It respects addition. Degree is the sum of all the orders, but also you have to weigh it by the degree of the point. So it's sigma AP times dP. And the kernel of this is clearly those divisors whose degree is 0. They will be somehow special. We'll call it div 0. Support is the number of points that actually appear. So the multiplicity can be, or the order can be positive or negative, integer. Then D is called integral or positive or effective if every order is non-negative. Okay, so essentially these poles you are avoiding. D, we say D greater than or equal to 0, and then we define this notion of division. So one divisor divides another divisor, D1 divides D2, if order wise orders of D2 are at least as big as that in D1. This division, you can actually think of it also what it means physically, because if you are thinking of order as a multiplicity of that particular 0 of that particular root, right, then we can say D1 divides D2 if the multiplicity in D2 is at least as big as the multiplicity in D1. So at the level of the function, this is somehow saying that F1 divides F2. But it's not quite that. This is much more abstract than that simple thing. Okay, so yeah, just to give you some more analogies. So integers, for example, are divisors of 0. In fact, the 0 ideal, if you think of the 0 ideal in the ring of integers, then 1 and 2 and 3 and all these, they are actually dividing the zero ideal. So that is the thing we are also trying to simulate over a curve now in a more abstract setting. So these points, the points P that are living in the divisor group, they divide the ideal of the curve, which for example can be x2 square minus x1 cube minus x1. Right, so these points are, remember, they are prime ideals. So these, what we are saying is that these prime ideals in the divisor, they divide the ideal which defines the curve. So in that sense, we can call it a divisor. Okay, so at least the points which are primes, they we can see this as the physical interpretation of the term divisor. But of course, that interpretation fails when you start doing this additively. So it's not clear if I take a prime P1 and I take another prime P2. Why should this be called a divisor? So yeah, at this point the physical interpretation fails, but at the level of point it is still true that points do divide, the prime ideals do divide, they are actually divisors of the ideal. So P1 plus P2 is kind of an abstract divisor. Of this, and instead of so in the case of integers, we actually multiply integers and they remain divisors. In the case of divisors of a curve, we will not multiply them, we will add them. Okay, so these are actually written additively, but the physical interpretation is supposed to be coming from really the way integers behave, and they give you a group.
So when you add these two divisors, P1 and P2,
written
the two prime ideals. So you add ideals and you get, when you are adding two prime ideals, you get the entire ring, right?
No. Maybe it's a good example. No. So this example has completely confused you. This addition is not ideal addition. It was a free abelian group that we had defined. This addition has no meaning. In all your mathematics, till now you have not seen any operation which corresponds to this addition. It's a completely abstract addition. You are just taking you take an animal like cow and you take an animal like goat, and then you take a formal sum of that. There is no operation between cow and goats, so you are just adding them. You are just saying that this is a new object. So which is what is happening here. P1 is some point and P2 is some other point, and we have just said that okay, I will start looking at their sums without defining what a sum is. It's just formal addition. In mathematical terms, you are just saying that P1 is a basis element, P2 is a basis element, and I can start taking formal sums, and I'll get infinitely many sums. There is no dependency between them. These are two independent objects. So which is why this very soon the analogy breaks, but we continue using the term divisor, and we write them additively. So these divisors written additively are actually new objects. And yeah, so varieties, or in this case curves, they give you these new mathematical objects with no physical interpretation, but we will soon see that actually it will we will be deriving some physical interpretation out of this object, but that will take some time. So after exam we will prove some theorems which will tell you that this new object actually carries fundamental geometric information about the curve. Okay, but that will take a lot of development of algebra. So for now, let's continue that development. So divisors are interesting. Because each rational function x in K star has an associated principal divisor. So we are defining principal divisor like this. So this is basically go over all the points of the curve, look at the valuation. Okay, this is one of the key objects which has inspired us to define the divisor group. For a rational function, you can look at the zeros and their multiplicities, or poles and their multiplicities. So it is because the point is actually, you can think about the DVR, the corresponding DVR, and then the uniformizer will give you the valuation map, and you can just put the valuation of the function x here. No. It means this is a definition. So the definition of principal divisor is this. This is the definition of principal divisor. Yeah, so this again is a formal object, but this has great physical interpretation, because this is just saying I'll take a formal sum of all the roots with multiplicity. Now, one thing you have to show that this definition is actually, it makes sense, because what you have to show is that this sum is not an infinite sum. Right? If it's an infinite sum, then this element will not live in div C. So why does it live in div C? Because this sum actually has only finitely many non-zero summands. Can you show that? Only for finitely many p. How do you show this? By now this should be easy for you. So valuation positive means that you are looking at the zeros of the function x, right? How many zeros can a function have? That can only be finite, because you are on a curve, so dimension is 1, x puts another constraint, so dimension becomes 0. So this system has only finitely many solutions, right? It cannot have, I mean, over the algebraically closed field also, you have only finitely many points. In other words, x only appears in finitely many MPs, the maximal ideals. We also saw that, right? So intersection of MP is 0. There is no element which appears in infinitely many MPs. So just note that valuation of x is 0 for all but finitely many valuations. Okay, C sub k is our is the abstract curve, or equivalently the set of all valuations. And if you go over all the valuations, you will see that the valuation is always 0 except for finitely many cases, and those are the ones that give you the p's. So p's are actually only finitely many, and so you have a finite sum. So it's an element, it's a genuine element in the divisor group. Is that clear? Okay, so let's see an example of principal divisors. So let us look at this curve. This is embedded in the projective space. So it has three variables. X0 is the homogenizing variable. It's actually basically the curve is just y square equal to what is that? Y square equal to x cube minus x, I think. Curve is simply that. It's an elliptic curve, happens to be an elliptic curve. Let's look at the function x1 over x2. So what is the principal divisor of this function, right? So you have to basically find the zeros and the poles and their multiplicities. Let's do that calculation. Yeah, so the first 0 is, let's try x1 equal to 0. So x1 equal to 0 means that on the curve, if x1 is 0, then it means that x2 square x0 is also 0. So you have two possibilities. You can take x0 also 0 or x2 also 0, right? So there are, let's take the first case. So x1 comma x0. Okay, because we are in the projective space, so you cannot set all the variables to 0, but you can set two of them to 0. So x0 equal to 0 implies, sorry, x1 equal to 0 implies that one of them have to be set 0. So we are setting x0 to 0, and x2 we are setting to 1, right? So that is the point. It's 0 comma 0 comma 1. That's P1. What is the uniformizer for this? Because we want to think of the valuation that this defines. So if you remember the calculations to find the uniformizer, what we do is we look at this curve equation and break it up into x0 and x1 parts. From that you can learn that either of these can be chosen as uniformizer. Let me pick just x1. So for the DVR, the unique maximal ideal is actually generated by x1, because you can see that x0 is a multiple of x1 from the equation. X0 is just a unit times x1. So x1 I take as the uniformizer, and that defines the valuation explicitly. So let's now check the valuation of f. So which is the valuation of x1 minus x2. What is the valuation of x1? Well, uniformizer is it x1 itself, so this is 1. And what is the valuation of x2? Well, x2 is 1, so valuation, it's a unit, so valuation is 0 with respect to anything. Right, so for this point, the valuation of the function is 1.
No, functions can have only 0 degree, right? The sum of the valuation should be 0.
How do you know? We haven't proved that in the class. Let us go on. Let us look at the next point. So the next point is x1 I have already set to 0. I had an option. Now I pick x2. So x1 comma x2. Right. So the point now is 1 comma 0 comma 0. I have set x0 to 1 and I have set x1 x2 to 0. What is the uniformizer for this? This is more interesting. Again, in the equation you see that x2 square is kind of equal to x1. Okay, to x2 square is equal to x1 up to units in the divisor ring for P2. So the uniformizer you can only take it to be x2 now. So it's just x2 and divisor, the DVR is RP2 with the valuation of, I mean basically this I can just write that x1 is like x2 square. In the DVR. This you can see from the equation of the curve. In other words, valuation of x1 is 2. So valuation of the function is valuation of x1 is 2 and valuation of x2 is 1. So you get 1. Okay, so you can see that both P1 and P2 are genuine zeros, multiplicity 1. They are simple zeros of the curve. What remains? Now we have to move to poles, right, which means x2 has to be set 0. If I set x2 to 0, then what do I get? From the equation I have to now either set x1 to 0, which we have already seen, that was P1. Other options are I set x1 minus x0 to 0 or x1 plus x2 to 0. So x1 plus x0 I set to 0. What is the uniformizer now? Yeah, so again similar calculation as for P2. You look at the equation, x2 square is kind of equal to x1 plus x0 up to units. So I again take x2 as the uniformizer in RP3 DVR. Okay, and what is valuation of the function now? It's again for x1, you will get what? What is this? Well, x1 actually will be a unit. Both x1 and x0 will be units. It's only their sum which is a 0. Right? x2 is 0, x1 is equal to minus x0, but clearly x0 and x1 cannot be 0, because if they are 0 then you are out of projective space. So you have to pick x1 and x0 to be 1 and minus 1. So both of them are units. So this valuation, first one is 0. What is the valuation of x2? That is 1. So you see that P3 is actually a simple pole of the function. Okay, what is the other option that we have left? So the only option now that we are left with is x2 comma x1 minus x0, which again, like before, is uniformizer will be x2 in now in the DVR RP4 with x2 square like x1 minus x0 up to units. In RP4 DVR, which means that the valuation of f is exactly like before. You get 0 minus 1 equal to minus 1. So what you have learnt is, this is a very illustrative example. So you have gotten all the zeros and the poles with their multiplicity. So P1, P2 are simple zeros and P3, P4 are simple poles, and there are no other zeros or poles on this curve for this function. So which means what? What is the divisor of f? It's P1 plus P2 minus P3 minus P4. Okay. Is that clear? That's the divisor in this abstract divisor group in diff C. Yeah, so now coming back to what Tujit was claiming in the very beginning without proof, is that the sum of order should be 0, which in this case is true. 1 plus 1 minus 1 minus 1 is 0, right? So we'll prove after the exams that this actually is a property which is always true for principal divisors, that degree of principal divisors is always 0. So the number of zeros and poles, they have to balance each other out. So degree of this is 0. So which also means that this principal divisor is in div 0C. So we'll actually prove that this is true for all principal divisors. Do you think that every divisor in div 0 is of this type? Is every divisor in div 0 coming from a rational function? So you have shown that every rational function lives in div 0. Is the converse true? Is this? Do you expect this? So this question is what will ultimately we'll formalize it, and we'll study this thing in great detail and depth. This question will lead to actually geometric pictures when or a geometric understanding when there is no geometry over finite fields. We'll actually show that this is not true for no interesting curve. Actually this thing will be true except the projective line. So it's only curves which are birational to the projective line that you will get div 0 equal to basically k. In all other cases div 0 will be bigger, which means that there will be degree 0 divisors which will not correspond to any rational function. It will be strictly bigger than k, big K, bigger than the function field. Okay, and how big it is, that will tell you how many holes there are in the curve, which we'll call genus. Okay, we'll measure those things. But it takes a lot of development, so don't get too excited. Okay, so let's just collect this, what we have deduced now. So let's call these principal divisors. Let's collect them and call it div AC. This is a subgroup of div C. Why is that? So you look at the set of all these principal divisors. It's an additive subgroup. So you have, suppose x and you add it to y. I'm claiming that x plus y is also in div AC. Why is that? What should I put here? In the blank space, what should you fill so that this divisor equation is correct? It's an identity. Just think in terms of zeros and multiplicity, right? If there is a 0 for x, p is a 0, so p appears in bracket x and p appears in bracket y, then p will also appear in, and you are adding it, so p plus p becomes 2p. So 2p should appear where? What is the function where the multiplicity of p is 2? You can take x square, or you can take y square, or you can take their product, x times y. So just take xy. This is the identity. Right? This is true for all functions. Right? You can check this by valuations. For any point, you look at VP both sides, and you will see that it matches. Okay, because we had this axiom in valuations that it is on multiplication, it is on product, it is additive. So it's just that. Follows from the valuation axiom. Is that clear? So immediately what we learn is we have now three groups. So we have a chain of subgroups, additive groups. This div A is a subgroup of div 0. Sorry, this I have not shown. Yeah, let me not claim it here. Right now I just know that this is a subgroup of div C, and div 0 is of course subgroup of div C. So these are the things we immediately know. That the set of principal divisors give you a subgroup and of the divisor group, and degree 0 also give you a subgroup. So our long term goal is to compare these subgroups and measure them. Okay, so we will actually want to develop a quantitative analysis or quantitative methods to say this properly, that is div A contained in div 0? If it is contained, how much smaller can it be, and so on. What is the geometric interpretation of that? So yeah, so to do that study we have to define few more things. So let's move in that direction. So we want to say that with respect to a divisor, two functions are called equivalent if so just take a cue from principal divisors. When would you want to call x and y congruent modulo some principal divisor d? When x minus y is a multiple of d, right? The function that d defines, if that divides x minus y, then so here we will write it as x minus y greater than equal to d. Or when d divides x minus y. Okay, so we are defining these things. So with respect to divisor, we can actually compare rational functions. We say that they are equivalent if you look at the zeros and poles of x minus y. Each of the orders should be at least that in D. Right? So in a sense, so when D is a principal divisor of f, then f should divide x minus y. So we are trying to mirror that here in general. We can also write it as D dividing x minus y, where D is a divisor and x minus y is a function. This actually is a equivalence relation. On K, on the function field. That is because well, x is congruent to x. If x is congruent to y, then phi is also congruent to x, and if x is congruent to y, y is congruent to z, then you basically have x minus phi greater than or equal to d and y minus z greater than or equal to d. You can sum this up and you will get x minus z is greater than or equal to 2d. Is that right? You don't want to do that. Yeah,
X minus
yeah, correct. So, yeah, you shouldn't do that. Let's just check it. So, x minus y and y minus z, they are greater than or equal to d. This means what? So, you should actually do this properly by using valuation. You should.
sum will be greater than or equals to d from the minimum. When you add two numbers, you get minimum of the derivation.
Correct, yeah. So, the valuation, if you look with respect to p of x minus z, so now we are using the second axiom of valuation, which is on sum, right? So, x minus y plus y minus z. This is greater than or equal to both x minus y and y minus z. So, ultimately it is greater than or equal to d. Is that fine? No, the axiom was what? You take the minimum.
Minimum.
Yeah, so I should put minimum here actually. It's not this strong. It's only for minimum. Sorry, this is order of, yeah. So, this will be greater than or equal to order of p in D that's the formal proof. Basically the valuation of x minus y is lower bounded by the valuation by the order in the divisor D, and the same thing is true also for y minus z. So hence the minimum will be lower bounded by the order of D with respect to P, which then means, since it is true for all the points, it means that x minus z is greater than or equal to D. Okay, so that's the second axiom of valuation. So you can classify, once you have a divisor in mind, D, you can actually classify the functions into classes, such that within a class all the functions they look the same mod D, and across classes they look different. Okay, yeah, is that clear? Fine, so we will now define a more important object. So now what we will do is given a divisor D, we want to study this approximation theorem, right? So remember the approximation theorem which we proved in the last class, which gave you, okay, so with this, yeah, so approximation theorem said that if you are given if you specify points with the multiplicities, then you can find a function which is lower bounded by that, right? So points with the multiplicities you can think of as the divisor, that's the input given to you. And approximation theorem says that there is a function which will be lower bounded by this function whose principal divisor will be lower bounded by this D. But we now what we want to do is we want to understand how many such functions are there. Okay, we want to restrict to those functions which pass through the approximation theorem. And to do this properly, we will define probably the most important object till now, which is this LD sheaf. So for a divisor D, LD to be all those functions, let me just skip this thing, just normal LD, to be the zero function and all the non-zero functions whose principal divisor is at least minus D. So we'll call it LD sheaf. Okay, without defining what a sheaf is, but if you already know what a sheaf is, then it will hopefully guide you in the correct direction. So this LD sheaf, for those who don't know what a sheaf is simply a subset of functions, including zero, whose principal divisor is greater than or equal to minus D. Now I can as well have, I could as well have done this to be plus D. I use minus D because the theorems later will become nicer looking. Okay, this D minus D isn't important. We just go with minus D. So in other words, what this is doing is that it collects functions whose poles are not any worse than D. Okay, so think of D as just point P. So what is the meaning of x greater than or equal to minus P? It just means that if you look at the poles of x, there is possibly only one pole and it can only be P with multiplicity 1, right? There cannot be any other pole, because if x has some other pole Q, then x will have minus Q, but minus Q cannot be greater than or equal to 0. Minus Q is strictly smaller than 0. So yeah, so what this is saying is that collect all those functions whose poles are not any worse than the zeros and the multiplicities that you see in D. This is what it is saying. Okay, so this is our LD sheaf, and I can define one more version of this because that will be better for quantitative estimates. For any subset of points, define a restricted divisor ds and we are thinking of some divisor d. So restriction of a divisor d with respect to s is just restricting to the points in S. Okay, so instead of going over all the points which appear in the support of divisor D, you restrict to the ones which are in this set S. Okay, this is called a restriction of a divisor by a subset of points. And I can define a restriction of the LD sheaf now. So this restriction of the LD sheaf is those functions which are correct on the S part. Okay, so here the difference here from the LD sheaf is that again, of course, this is saying a similar thing, that poles of X are not worse than D, but only up to the points in S. Okay, this is only comparing the points which are in S. So if P is in S, then if P is a pole, its multiplicity should be at least minus of the multiplicity of P in D. But if P is not in S, then we don't care. Okay, then this is not putting any constraint. So that is the difference.
So to define this L space as LD, so the support of divisor should be the same as the support of the functions living in that space, right? So that is why this subset is defined.
See that again?
This space LD.
Yeah.
So the support of the divisor D has to be same as the support of the principal divisors that are in this space. So that is why you are defining this LD underscore S notation.
I did not understand. What do you mean? D is arbitrary and S is arbitrary. There is no requirement here.
No, suppose D has a support a subset S.
Can be any support. Doesn't matter. Wouldn't so. If if S is disjoint to the support of D, then D restricted to S is just 0. So then this is just saying that collect all the functions X which and so X sub S means that you are only looking at the points which are present in S. Those can only be zeros. They cannot be poles. Maybe we should take this as an example. It's a good example. So example, if you take S disjoint from the support of D, then X is in LDS if and only if, so non-zero X's, if and only if this X sub S is greater than equal to 0, right, which is like saying, which is exactly saying that the points which are in S, on them you want your rational function to either vanish So let's write that. For all the points in S, you want the valuation of x in those points to be greater than or equal to 0. So either these, I mean basically then x has to be in the DVR. That's what it's saying. Okay, let's just write this. X has to be then in the intersection of DVRs. So the points which are in S, you want x to be in that DVR, so you take the intersection. Right? That's the illuminating example you have. This is what LD restricted to S is doing if you take S disjoint from the support of D. If there is a point common between S and the support, then you will have a different condition. Then you will be talking about poles. Here you are avoiding poles. You are saying that poles are not allowed from the points in S. Greater than or equal to 0 means that either P is a 0 or it is neither a 0 nor a pole. Right, and so this is a big difference from LD. In the LD sheaf, you will have more functions, right? Because there you are not restricting to S. You are actually. Sorry, I'm making a mistake. Yeah, right, smaller. Let's write that down. So LD will be smaller than LDS. Why is that? Yeah, so if x is greater than or equal to minus d, then it means that x restricted on S is also greater than or equal to minus ds. Okay, so whatever x you have in LD, that is trivially in LDS. But as you can see in some examples, LDS will be bigger. So although you are, I mean, I'm saying it to be a restricted LD sheaf, in terms of size, it's actually bigger. Any questions? Okay, so let's see more properties, because this already is actually you will see many interesting properties which are easy to show. So LDS is a K vector space. So this is not just a subset of the function field, it's actually a vector space. It's a subspace of the function field. Why is that? If there is a function x, there is a function y in LDS. You have to show that x bracket x plus bracket y is also there, right? So again, it follows from the valuation axioms. If D1 is greater than or equal to D2, then what can you say about LD1S and LD2S? How do you compare them? So D1 may have more points and more multiplicities, bigger multiplicities, right? So it seems that you are putting more constraints on the functions. So it seems that LD1S should be smaller, but that is not the case because you have to remember we have a minus sign. So you are looking at functions which are greater than or equal to minus D1. So it will be the opposite. So you will actually have LD1S bigger. Okay, so minus sign actually helps us in getting this property. So D1 greater than or equal to D2 means that functions which are in LD2S are already in LD1S. And similar thing for the subset. How will you compare these? LDS and LDS prime. You can use a similar intuition. So S has fewer points, so fewer constraints. So LDS should be bigger. That is actually true. And what if DS and DS prime are equal? Sorry, D. So for D and D prime, if for these arbitrary divisors the S part is the same, then clearly LDS and LD prime S, they will also be the same. Okay, let's quickly prove these. Why is it a vector space? If for a point the valuation of functions x and y is at least minus d, then you understand the valuation of their sum also. For any small k combination. Right, if the valuation of functions x and y is at least some value, then the valuation of the sum of these functions for any linear combination by the valuation axiom is also that, which means that this if x and y are in LDS, then alpha x plus beta y is also in LDS. Right, so you are done. Fine. Yeah, so you can sum up rational functions in LDS, you remain there. Second property, so if xs is at least minus d2s, so take any element in LD2s, which means that xs is at least minus d2s. Minus d2 is greater than or equal to d1s. Which means that x is also in LD1s. Is that fine? So here you use the minus sign that we have in the definition. Okay, I think others are easy. So that gives you all the properties. Okay, these are simple properties. Okay, so next thing that we will do is remember we want to do a quantitative study, which means that second property, which is saying that if you take a bigger divisor, then the restricted space, the LD sheaf gets bigger. We want to actually measure how much bigger will it get. Okay, and we'll do this now quite precisely. So we want to measure how big is LD prime compared to LD. Now both are vector spaces, so we will of course measure their dimensions. Okay, so what is the oh, in fact LD is a subspace of LD prime, right? So we'll just want to we basically want to compute the dimension of LD prime mod LD, that quotient vector space. So that's a major theorem. So let's have this. So we have the setting is S is finite, set of points on the curve, and we have this d prime greater than or equal to d on the restricted points S. Then this dimension of the quotient space can you guess what this is equal to? LD prime S mod LDS. So this will be given by the degree. So degree of ds prime minus degree of ds. So in a way, the more points you add in d prime over d, for every point the dimension grows by 1. Okay, so per degree this LD sheaf is growing by dimension 1. This is what we want to show. So we will show this by induction on the degree essentially. Okay, we will induct on how many these points you see in d prime minus d. Starting with 1, our base case would be that. we'll use the finiteness of S to invoke the approximation theorem. Since these points are finite, the set S is finite, we can invoke the approximation theorem for finitely many points give you these finitely many valuations, and that will give us the functions we want in the proof. Approximation theorem on valuations for P in S. That is the plan. So here actually the base case will be the hard case, induction step will be easy. So base case is the case of a single point growth of D prime over D. So we'll do that later. The induction step will actually be easy, which is let this growth be by many points Qi's 1 to h. Two or more points. We can actually reduce this to a single point growth, which is h equal to 1. So how do you do that? You basically look at these divisors which you are getting when you add q1, then q2, then q3 dot dot qh. So you have a tower of space. Which is LDS is contained in LD plus Q1S dot dot Q1 QH S, which is LD prime. Okay, so we divide the vector spaces LD prime S and LDS into this tower of subspaces by the proposition. Is that correct? So when the divisor grows, the space also grows. The L sheaf, LD sheaf grows. And then we use the base case for every step here. So what does that give you? So this means that dimension of LD prime S mod LDS over the base field K is equal to so actually this is this will just follow from linear algebra. You have a sequence of vector spaces strictly growing. If you know the dimension of each of these quotients in the middle, then the sum will be the total dimension. Right? This is just like Gaussian elimination or growth of a basis. You find the basis of LDS, then you grow it by 1, then you grow it by something to get to the next one, and then you grow again to get to the next one, and so on. So just grow the basis and you get this sum. and this is one less. Okay, so I equal to 1 means LD plus Q1 mod LD, and then I equal to, you go up to I equal to H, which is LD plus Q1 to QH, which is LD prime mod, S mod the previous one. Okay, so that's the dimension that you have grown up to, which by base case is just degree of Qi. Which ultimately is equal to degree of this. Is that clear? So induction step is pretty easy, just growth of the basis one point at a time. So all we have to show is that in the first step, when you go from D to D plus Q1, the dimension growth is degree of Q1. If we show that, then we are done with the theorem. So that's the claim. So dimension of L D plus QS mod LDS is equal to degree of Q, always. Okay, for any divisor D, for any point Q, and for any subset of points, finite subset of points S, this is true on the curve. Yeah, I think this will take longer, so maybe we have to stop now. The idea of this is not very hard, but there is some calculation to be done. So idea is just that let your points in S be P1 to Pn. Remember that in this setting Q is in S, right? Q is in S. So P1 is the Q, and then you have more points P2 to Pn. That's your finite set S. And degree of Q is D, let's say. That is the setting you are in. So when you add another constraint for the functions that you are looking for, basically the constraint is this minus Q that you are adding in the constraint. So how much does the set of functions grow? So you want to show that they grow by exactly D, the degree of that point. In particular, think of degree being 1. You actually have a real point Q. In that case, degree is 1. So you want to show that there is only one new function that you will add. Okay, that's what you want to show. When small d is equal to 1, then just one new function appears. So where does that function appear from? So it actually appears from the DVR of Q. That is the idea. So we will develop the basis, the K basis by using that of the DVR. Corresponding residue field actually. So you basically look at the DVR corresponding to that point. Proof idea is that in that DVR, I will be able to find a function which will be new. That's all. Okay, but implementing this proof idea will take much longer, because obviously somewhere we have to use the approximation theorem and all that. So let's do that after the exam.